Okay, so let's start the class today. And today we are continue our problem regarding the clustering problem that we started previous time. So we talk about clustering algorithms that you are given a graph, you are given a set of vertices or nodes and some metric on them, and you try to cluster them because clustering is generally very important. Tons of applications. As I mentioned, the whole unsupervised learning, somehow the people consider it equivalent of clustering. So you try to get whole data. So this is the whole data that you have, and you try to cluster it into some smaller things, and you can do lots of things. You can, among like algorithmically, you can do divide and conquer, or you may want to process each of these clusters essentially for different reasons. These are like each cluster you can consider a similar set of people. So it's one of the most important things in the network design and network algorithm is the cluster. We talk about two important algorithms there, K-center and K-median, that for which we could actually prove approximation algorithms. K-median actually, as I mentioned, is very similar to the another problem called facility locations. I mentioned that for K-median, if you have capacities, then on each center, then the problem actually is open with there's a constant factor approximation on that. But that problem, for example, can be solved for the facility location problem, which can be considered somehow like kind of price collecting version or like Gaussian relaxation of K-median. But let's start with the problem here. So what is the uncapacitated metric uncapacitated facility location problem? Good. A little bit closer. Okay, good. So in the uncapacitated facility location, you are given a graph G and a metric cost on the edges, C of E. So you are given this graph G, and then there are, some C of E, which is the cost of this edge. And assume that you have a so you have a set of this is the cost, this is the connection cost that we talked before also at rent or buy. In addition, we have two other sets. We have this set D and we have this set F. It can actually have intersection, or D and F potentially, so D and F are subset of V, but in particular they can be open to. E is a set of essentially demands, clients that they have the demands, and F is the potential places in this metric that you want to open a facility. You can think about the K-center problem that we have mentioned, or like K-median problem, that there you want to open K facilities, and then each person should go to the closest facility. In the K-median problem, which is actually very similar to this uncapacitated facility location, there was no opening cost for facilities. And you want to open at most K. Here, you don't have that limitation that you should open K. Instead, this is some kind of relaxation. You can open more facilities, but for each of them, you need to pay the opening cost. But other than that, there is not much difference between these two problems. And still, when you open these facilities, each client in this demand set D will go essentially to the closest facility. So the goal, what is the main goal? The main goal is to find the best set of facilities to open. And again, when you know that which facilities you want to open, then the clients, they know that to which facility they should go. They always go to the one that has is closest to them. That's the reason. And there is no capacities for facilities, so we can actually solve the capacitated facility location with a constant factor approximation. That's one thing. And the other one is the metricity. So this connection cost, that is very important, the same thing that we had, it is a metric. So essentially, I mean, this, and we have defined the metric, especially this connection cost have triangle inequality. So if this is A, B, C, if you want to go directly from A to C, it is not worse than if you go from, not worse than if you go from A to B and from B to C. So it is essentially C of A to C is less than or equal to C of AB plus C of BC. That's essentially triangle inequality that we are using from the metricity. Okay, so how can we write the problem with a linear program? So this is one of the problems for which we are using actually linear programming and rounding a linear program to solve it. Good. So what is the objective function here? Here, the first objective is that you want to minimize. So for those, f of I essentially says that whether this facility I is open or not. So this is actually one thing that should be here. This should be f of I times yi. So f of I is actually the cost of the facility I. And again, you can assume without loss of generality or not much loss of generality that f and d are equal to v. So for each yi means that whether you are opening the facility I or not. So you want to minimize sum of fi yi. So those facilities that you open, you need to pay the essentially opening cost fi. So fi, this is the opening cost. And now, what about for others? For others, you want to go, so for all other things, for any I that you have in as a facility, and any client J, and this is the demand, the DJ is the demand associated with client J. You will pay the connection cost, xij, if I is assigned to, so essentially if xij essentially says if client J is assigned to facility I. So that's xij is equal to 1. In that case, you are. Not that we already talk about rent or buy things essentially. Here, I mean, this is a demand DJ. You can assume that actually without loss of generality, the DJs are one other. Why? Because you can have several demands on one vertex. So DJs are not that important. And here, you know that potentially you may send essentially, this is the some client J. You may send part of its demand to this, part of its demand to this, and part of its demand to this. But you know that because there is no capacities for facilities. I mean, if you are sending for this J, the demand goes to several of these guys, you can always go to the one which is closest and you minimize the cost. So you know that in the integral solution, you just go to the closest. But this may not happen in the, so xij would be essentially only one for one facility, which is closest to it. But this might be not the case in the fractional solution. So what is the objective? The objective is that, as I mentioned, so this guy, it makes sense, this is the xij for different I, for example, xi prime j and xi double prime ij. So we want that some of these demands, like this, should be served at least one by this facility. So that's the important thing. Then xij, as I mentioned, in integer case, also the same thing also for yi's, they should belong to 0, 1. So the facility either should be 1 or 0, and xij, it means that this person should be assigned, if assigned to one facility would be 1, otherwise would be 0. Last but not least, this thing that we had this one also in the multi-commodity, this is the one that we taught it, multi-commodity Bayat-Bach. It says xij should be less than or equal to yi. What does it mean? It means that if this facility is open, then client j can open to that. So if the facility I is open, then xij can be 1. It means that a client j can be connected to that. Otherwise, if it is 0, then it should be 0. So you can, all of them, it makes sense when xij are 0 or 1 are integers. However, when you make it fractional, the question is that, I mean, you may not be able to satisfy all of them. And the question is that when we get a fractional solution for this LP, this is the procedure which is called rounding an LP. How can we round this LP from a fractional solution to an integer solution? This one can solve it easily by lots of linear program solvers, particular Pulp, Python, or CPLX or Groovy. But the question is that the solution that you may obtain, it might be not integral. And this is the question, how can we solve this problem? How can we make it integral? Without, and another thing, when we, essentially when we are doing this integer program to a linear program, the only thing that we are changing is this one. We say that xij's, or it should be between 1 and 0. The same for y. So this should be yi's between 1 and 0. So the only condition that we need to put it there. And then we are good to go to solve it as a linear program. So we just relax it. And usually, actually, in the linear program, you don't need to even put this part, because you can see that xij never becomes more than 1, because you will lose. Same thing here. Yi's never become more than 1 in an optimum substance. So you don't need to put this one, just the xij is greater than. Okay, so let me clean everything. So again, this was the yi's. So this metric, this is the one that we try to show. This say that metric uncapacitated facility location has indeed a constant factor approximation. It shows this one for K median before, and there are some triangle inequality that we use, similar things we are using here. So as we discussed, the main issue is that, so we are solving this problem, and the fact that xij's are essentially at most 1, that is good, and it might be assigned to several things. The main issue is that these yi's, they may become fractional. If we can somehow handle these yi's, make sure that we can make them integral with not much cost, then xij's actually are not the hardest part. However, to do that, because yi's are somehow forced here, you see here, yi's are actually forced to be large because of xij's. So we need to also somehow massage xij's. Good. So let's go and see what can we do here. Okay. So this concept of G-closeness, we need to define. What's the meaning of G-closeness? So, or you are saying that you are given a value Gj for any client J. So essentially G here is a vector of G1, G2 to G size of T, or say Gn essentially. We say a feasible solution xy. A feasible solution is a solution to that LP, it's a fraction. Is G closed if we have this property? If whenever xij is greater than 0, xij is between 0 and 1, and it can be fractional because it's fractional. But we want to say that whenever xij is greater than 0, then we have cij's less than or equal to gj. Essentially, if you consider this ball around j, gj, you want to make sure that anyone here, x, I don't know, kj, these guys which are outside of this ball, they should be 0. So it means that essentially we have this G closeness property. So what can we do here? For a client J, store all the facilities essentially. Again, you can consider facilities and clients, these are the whole set of vertices. Each vertex can be a client or can be a facility, or both. So you will consider for each client, sort them according to their CIJs. So if pi1j is the closest facility to j, then the second one is this one, and the last one is this. So we are assuming there's, I mean, for each client, we can just sort. So this is the one essentially. So this is the client j, and then so this one is essentially pi1, this one pi2, and this one pi3, and so on. So they become further and further from this. The second one that I want to define is the concept of alpha point. The alpha point for a client J is defined as Cj alpha, which is equal to some C pi of I star J. What is the I star? I star is the one that if you sum the xij's according to this order, according to pi i's, up to I, all the xij's, the sum of the xij's would be greater than or equal to alpha. So in some sense, it means that if you consider the people from here, this is, for example, pi3, and so on, and maybe actually this is the I star. The thing is that if you just sum over all of these xi's to here, sum of the xi's, so this is the ji. Some of them are greater than equal to alpha. I is equal to 1 to, and this is the minimum I. So the first time that the amount of serving that we are doing for client J, some of the xj is essentially the serving amount. So the first I, that the serving amount up to this first I star facility is at least equal to alpha. So in some sense, you can say Cj alpha is some kind of intuition, gives us somehow alpha fraction of the ball centered in J. So if you consider the complete thing, you may go very far thing that is assigned to them because of whatever reason in the LP. But this one essentially is talking about the alpha part. What would be the value of alpha? Alpha would be some constant that we will decide later. Now, let us so here define this as equal to all those guys that Cij is greater than Cj of alpha. Good. So S is those guys. So this is essentially if you define this for this case that we have. Essentially here, this Gj would be, say, for example, is equal to C I star J. So if this is the Gj, S would be everyone. So what is S is everyone here, including on the boundary. So that is important here. Why? Because we want to have this property. We know that some of the xij's that are outside of this ball is greater than or equal to 1 minus alpha. 1 minus alpha, because I think the main thing is that this set also includes I star. So S here, so S include I star. This is important, otherwise we didn't have 1 minus alpha. Because it includes I star, then we have some of the xij's greater than 1 minus alpha. So essentially, this is some kind of radius that we are defining according to the alpha. This is the alpha fraction essentially inside this ball is served, and the rest 1 minus alpha. So that's essentially the idea. So it's somehow like when you are sorting these facilities by their distance to this client, according to the alpha, it means that what is the radius of the ball that alpha fractions of the demand is served. And again, you can assume that the actual demand dj that we had it before is just 1 at this point. Not much difference. This is the part that alpha fraction is served, and the 1 minus alpha is served outside. That's it. So what do we have here? So we have these equations that we were using it. Sum of xij, cij, I belongs to f, is greater than those that are belong to S, because S is a subset of F. And then that is greater than or equal to 1 minus alpha times Cj alpha. Why? Because for these guys, we know that Cij's, so this is essentially, you can just write it like this. You can say, right, this one you can say that this would be greater than Xij. Here, what I can write it Cj alpha. Why Cj alpha? Because we know that Cj alpha is greater than Cij. That's by definition. Now I will just take this Cij out of this sum, and then some of the xij's by the definition of S, I know that it is at least 1 minus alpha, and this Cij is the one that I took it out of the summations. So I have these things. So what do I have? I have Cji is less than or equal to 1 minus 1 over alpha times Xij Cij. So in some sense, actually, Cji is the average connection cost. If I write this one, then from this one, so I can say that this is some kinds of the average connection costs that I'm dealing with. I mean, essentially by this kind of average, 1 over 1 minus. So far we have just defined this essentially Cj alpha for any given alpha should be constant later decided. We have this equation that I have mentioned. And we have, what is the goal? The goal is that now we want to, as I mentioned, this Cj alpha would be, these are the Gj closeness that we are talking about. Now, let's consider the whole xy, that is from the fractional solution. From that, I want to get a feasible solution, x bar and y bar, such that these are Cj alpha close. What's the meaning of that? It means that all these facilities who are serving a client would be Cj alpha close to that client. And we want to say that we are not losing too much in terms of the total cost. Good. So, as I mentioned, alpha would be some constant between 0 and 1 that we decide later. We can, so this is the lemma essentially. We can change xy to find a feasible solution x bar y bar, which is Cj alpha close. And we have these equations. What is the equation that we have? Sum of the y bars. So we get essentially yi bar. So we are changing essentially who are the open facilities. That's the important one. But we know that the sum of the facility cost of these people would be not more than 1 over alpha this. Note that alpha is less than or equal to 1. So this factor would be greater than or equal to 1. But it is controlled by essentially 1 over alpha. So the facility cost in this new instance that we will get it would be 1 over alpha times the original facility. Okay. Let's So what do we do here? For each j, for each client j, let alpha j essentially be some of these xij's of those people which are less than or equal to say j alpha that we have defined before. This alpha point essentially. Now, so this is the alpha j point that, so alpha j is the sum of these points essentially. Cj alpha is the alpha point and alpha j is actual alpha. It might be a little bit more than alpha because so that it should be at least alpha. Then what do we do? If Cij is less than Cj alpha, so essentially it means that if you consider this j, is this I is inside this ball and the radius of this ball is, this is the radius of the ball, which is Cj alpha. So if this is inside the ball, then the Xij will go up by this factor alpha j. So it will be divided by alpha j. Alpha j is less than 1. So this would be a little bit, so essentially you are serving this guy a little bit more with this I. Before it was xij, now you are changing it to xij over alpha j. Otherwise, it would be 0. So for everyone else, it would be 0. Good. Now, what will happen? So we satisfy everyone because we have divided by alpha j here. So everything is satisfied inside, nothing outside. What about in terms of facilities? What did change essentially regarding the facility cost? So for the facilities, also I defined yi to be mean of yi over alpha and 1. So as I mentioned, alpha yi's cannot be more than 1. Why do I do this one? The main thing that I'm doing this essentially this alpha things is that I want to make sure that this xij now essentially comes to this I. Maybe this I, the amount that I have opened it was not enough. So I have just, for example, so this xij, it might be just was equal to yi. Because the only condition that I have is that xij is less than or equal to yi. Now, you are essentially blowing up xij by this alpha j. I need to do the same thing here by some alpha. And this would be actually greater than this one because alpha is less than or equal to alpha j. So I need to also blow up, and essentially you can think about alpha j's are equal to alpha. So I'm blowing up xij's. I need to blow up also yi, and of course it should be at most 1. I don't want anything more than 1. Then in this case, I mean, we are satisfying everything. So we are satisfying our LP requirements. Why? If you see the LP requirements, so we want to just essentially say that xij is equal to 1, which is the case because of this blowing up. And I wanted to have xij less than yi, which is the case here. And again, I mean, this is important. Alpha j is greater than or equal to alpha. So in some sense, for example, you can think about xij is divided by 1/2 versus yi is divided by 1/3. In this case, you will see that yi goes at least it's the same factor that xij goes up. So we are satisfying this. Good. Now, so what did happen? So essentially, we consider this solution xij yij. From that, we got this solution, this new solution y bar, x bar, y bar. And what did we do? Essentially, we had some kinds of concentration or like more toward the average thing. Anything which is outside of this, it might be a little bit xij goes to a very small amount. It may go epsilon to outside of this ball. We will just make all of them are 0, and we have adjusted those facilities should be opened accordingly. Now that I have this property, I want to go to the next step. And what do I want to say here? I want to say that given a feasible fractional G-closed solution that I have it now at x bar y bar, I can find a feasible integral solution, which is 3G closed solution, and has this property that here, essentially the facility cost will not go up. Before, the facility cost already went up essentially here because of this dividing by alpha. As I mentioned, alpha would be constant. However, from this solution that I obtained, I can find another solution that the facility cost does not go up. Here, the connection cost actually may go up, but I will bound that one. But the facility cost in the previous case, only the facility cost went by factor alpha up. And then I want to say that nothing happens now to the facility cost anymore, but the connection cost may go up. Here, actually, I didn't, in the previous case, I didn't increase the connection cost because all the connection actually was less than or equal to previous case. Good. I essentially put anything outside of that ball that was connected to something inside. So I didn't lose anything in terms of connection cost. I just lost in terms of facility cost. Here, I'm losing in terms of connection cost. I will say the facility does not. So, okay. So let's consider F hat, which is a set of facilities that are partially open. What's the meaning of partially? So this is if we have just done this change from so we have this solution. Now there are some facilities here that are their opening is not 0 or 1. If 0 means that essentially not open. If y equal to 1, it means completely open. So we are fine with that. These are already integral. The only problems are those that are between 0 and 1. You need to handle them. These are the partials. Now, say consider this guy I, which is the yi is between that, and what is the issue? The issue is that this guy is serving some clients j. And again, these are like, if you consider the set of all of this kind of partial guys, not just one of them, this is f hat, and then what are these d hat? D hat are those guys that are served by these f guys. So we need to decide something for these f hat bars, f hats, because they are partial. So this is exactly the concept of rounding. We need to round either to 0 or 1. Either we need to completely close or open. And we want to do it in a such way that the total facility cost, which is the fi times those yi, does not go up. So we need to handle this d hat. There is no other way. So essentially, d hat is the set of, so these are I know that these are the guys that they are going xij, that they have it for this, that should be greater than 0. These are the clients that are served this. Otherwise, it's 0, we don't consider. And here, what was the gj? The gj would be equal to cj alpha from the definition that we had it before. So gj is equal to cj alpha. It's alpha point that we already decided. And g is the vector of gjs. Okay. So we can just so let's go to the next one. Now, what do we do? Again, consider this d hat. And as I mentioned, the gj is defined to their cj alpha. This is some kind of average connection cost. So what do? I will sort these guys. So I will sort d hat. So I'm sorting d hat according to gj. So we will sort them according to this average connection cost, essentially, or gj. I will handle these guys. This is very similar to the same thing that we discussed previous time for K-median. When we talk about local search, we said that in the local search, we have a set of swaps. And then we want to say that if we want to do swaps, so some facility, we may replace it with another facility. So those guys which are assigned to this facility in our solution should be assigned to some other facilities in our solution. Because or to the corresponding facility in the optimum, we try to do that. So we are doing the same thing, and there we use the triangle inequality. We are using the triangle inequality again here. Triangle inequality generally give a factor 2 or 3, essentially. That's a typical thing when we use the triangle. Okay. Let me just do this one. Actually, is better things. So let me just say this one then. So consider a client J prime in D hat. So this is a client J prime in D hat. And again, these are sorted according to their GJs. Now, so this is a J prime. This is the one that we are considering here. Now, let's define the Sj with those guys that Xij is greater than or equal to 0. X hat of J prime. So this is the one that we have so far, we have defined. And we know that everything, so we know that outside this ball, S of J, that should be 0. That is by the definition of G closeness. So this is the set of currently open facilities that J is connected. Okay, so among these guys, we will close all but one of them. So among these guys, this is the Gj prime. Here, let I let I prime be the facility with the minimum opening cost. Well, actually, this maybe I want to just change this one. This is say I1. This one says I prime. What do I do? So this instead of X, I will just use. So this is I1, this is I prime. So who do I open? I want to, among all these guys, I don't want to pay extra facility cost. I will open the person with the minimum opening cost among all these guys. Of course, if you do that and the sum of this Xij is greater than 1, so here the facility cost does not go up. We will assign J completely to this one. It means that this set of this Y, we will put of Y hat of J prime is equal to 1. And for everyone else, we will put it 0. And then we will put xij's accordingly. So it means that what's the meaning of that is, so this guy would be essentially xij of this guy. X of I prime j prime would be 1, and everything else would be 0. Good. So now what will happen? So what is the issue now here that we are doing that? So everything is fine. The only issue is this one now. So far, I mean, we didn't add anything to the facility cost. The only problem is that, I mean, this guy, for example, I1, that now we will put y of I1 equal to 0. So y of I1 now it becomes 0. What is the problem? The problem is that maybe some other facility J, some other demand J, it is connected to this guy. So it has some, so x of essentially I1 J is greater than 0. But because they are sorted, we are sorting essentially facilities in D hat, we know that the Gj should be greater than or equal to Gj prime. That is very important. But this is the problem that we have it here. So what is the issue? So the issue is that this y I1 was greater than 0 before. Because of that, this x of I1j was greater than 0. But now you will make it 0. But what should we do essentially with this j facility is connected there? The main point is that gj is greater than g of j prime. Okay, so what do? We are doing very similar again to the thing that we have done it for k median. We simply connect say that, okay, now I cannot assign anything to here. I will this j guy, I completely assign it to this I prime. So instead of assigning partially to here, I will assign it to this open facility in the ball corresponding to j prime. How much extra I will pay? Easy. So here I just use essentially triangle inequality. So here I will pay this, the radius of this was g of j prime. So I will pay g of j prime here. I will pay g of j prime here. And I will pay g of j here. So I pay essentially gj plus 2 times g of j prime. But I knew that g of j is greater than g of j prime. So what do I know? So the total cost that I'm paying would be at most 3 times g of j. And that's it. So the connection cost because of this for those guys that are now assigned to this, it would be 3 times the connection cost. And note that here, this guy, the y of this guy, essentially, this was I prime. This essentially becomes 1. This other guy becomes 0. So this will be out of equations anymore because these are integral. We don't touch them. And these guys are assigned also fully to these ones. So we don't touch them. We don't touch their facilities. We don't touch their connection costs. And everything is fine. And by the way, when we connect this guy to these things, essentially we are doing the whole xij to this guy. And we are not, so the connection cost essentially goes by a factor 3 up. So let me clear everything. Now that we have the whole things. This is the one that I have mentioned. So the connection cost essentially goes at most by a factor 3 up. So what is the total thing that we have? So what we have done is, so we have just first consider this one. So we made sure that essentially everything is like more concentrated and essentially on the average instead of very far from part. Then after that, we have essentially made this solution. We round it to integral solution, just making it 1 and 0. Now, how much we are paying essentially in total? This is the total cost that we have it here. The connection cost didn't go up because of this one. We were taking just the minimum guy. So the connection didn't go up, the facility cost. But the connection, so in the first essentially transformation, the connection cost didn't go up, but the facility cost went go up by factor 1 over alpha. In the first one, the connection didn't go up, but in the second one, the facility cost didn't go up, but the connection cost went up by factor 3. So here, and we just replace essentially Cj alpha with the corresponding things that we had it, which was 1 over 1 minus alpha. This is from the equation that we had it before, this equation that we computed before. And so this would be the final things. Now, one way essentially to get the final solution, we can put these two coefficients equal. So if you put it alpha equal to 3 over 1 minus alpha, you get it alpha equal to 1 over 4. So these two would be the same thing. This would be essentially 4. This would be 4. Would be 4 times this. Would be 4 times the optimum solution, and we get for approximation for the problem. So this concludes the proof, and it is 3 approximations. And now, is this the 4 is the best approximation? I mean, 4 is like, this is like one of the nicest algorithm for this and clean algorithm, but you can improve over 4. So if instead of this alpha, this is the technique by Gomans essentially, that instead of taking this is some kind of magic. Instead of taking alpha, if you put it just equality and compute alpha, you can take alpha according to some distribution, randomly from some distributions. You can write the equation, and in that case, you will get 3.1 over 6. So whenever these are these equalities, you can, one way is to just put these things equal to get one results. But another way is that actually you will take this alpha at random according to some distribution. Again, this is some technique that is being used by Gomans, and it has been used for price collecting problem first, but it has application in several other cases. Then you get 3.16. But you can actually get more than that. The current lower bound that we have it is the lower bound is 1.463 for facility. And this is under the assumption that NP is not subset of essentially deterministic time into the polylag. So essentially, we cannot solve NP in, this is called quasi-polynomial time, in quasi-polynomial. Some reasonable complexity, some complexity assumption. Before it was the previous one was the Birka that he had 1.5, and now it is actually there is 1.48 by Chile. I think this is the best current one, 1.46. It might be some slight improvement, but anyhow, we are very close now. And there are lots of papers, essentially. There are lots of techniques. So in that sense, facility location it has been a bed frame for doing lots of algorithms, essentially for LP rounding, as well as some of this local search. But dual fitting, lots of technique has been used. But this was one of the cleanest one that I have mentioned. This has been improved to 1.48 as the current best things. I believe, and it is very close, 1.46. There were lots of soda fox stock papers that just improving slightly from this, 4 and this. We get a constant factor here, but then we can improve. Good. So this is the one that we are done essentially with the facility location. Get a constant factor. And this was essentially somehow concluding the parts that we were talking about clustering problems. At least, this, we talk about K-center problem, simple to approximation, then K-median, you could get 5, and then you could improve it to 3, and some LP rounding, you could get 2.68, and then facility location, which is somehow relaxing this one. And actually the facility, hard capacity, this is the capacitated facility location, that each of these have a capacities that you can actually solve it. And again, why we can solve it and not for K-median? Because the K-median, there is a hard constraint that you can open at most K facilities. Here we don't have it. We have this kind of price collecting or essentially Lagrangian relaxation that yes, you can open more than K, but then you need to pay more cost essentially. So it is more soft constraints here versus hard constraints that we had it for the K-median. And for that, we don't know whether capacitated version has a constant factor or not. Big open problem. Now, I want to shift here. This is again, So this kind of clustering problems, these are like some of the facility location or K-median center. They are actually connected to this Steiner tree or connectivity problems through this problem connected facility location. So I will talk about the connected facility location, and there are nice algorithms there, and then I will talk about, some more about some of this Steiner tree problems. Like we talk about primal dual for Steiner tree or Steiner forest problem. These are very important, and these are essentially very important and very basic algorithm that the technique has been used for lots of other problems. So that's the reason that we are considering. These are very famous and very important network problems anyhow. So connected facility location is the one that actually connects facility location to Steiner tree. Not only that, but also it actually connects it to the rent or buy at bulk that we talked before. And the techniques are also beautiful here, the algorithms here. There are some very beautiful, nice randomized algorithms here that we will talk. So what is the connected facility location problem here? So here you are given a graph G, again, a metric cost seat, the same as facility location. Essentially, what is the idea? So before we had this graph, we opened some of these facilities. Now, I want to essentially I want to open some facilities. And instead of the connection cost, you can also consider the connection cost. So you always have this kind of, you have connection cost. But instead of opening cost for these facilities, I may want to consider the cost of connecting all these facilities together. And this is the one that Steiner tree problem is coming. So you want to essentially open a set of facilities, connect the rest of clients to these facilities, and you want to create a backbone among your facilities, and you want to pay the cost of this backbone. And this is important because, I mean, you want to connect these guys. This is very natural. So you can think about this connection cost, essentially the cost that you are paying from your house to one of these internet companies' server. And then they have their own backbone. And you want to minimize the total cost. So here we have a set of clients, D. Again, D can be equal to V. Consider that a facility can be opened at a client vertex. Again, assume that, I mean, D and V are equal. Each client has an associated demand DI. You can assume that DI is equal to 1, that you can actually do reduction with that. There is no opening facility opening cost out. It is not hard actually to introduce and get essentially similar, if not the same, approximation factor. The task is to connect each client to a facility. So this is the connection cost that we talk about it. Additionally, all open facilities need to be connected to each other via higher cost edges. This is the Steiner cost, essentially. Why we call it Steiner cost? Because essentially these facilities that you are opening, you need to connect them. And the cost of this one, these are like a broadband thing. So the cost would be higher. So we formally, essentially, so what is the one that you try to minimize? You try to minimize. Good. So assume that each edge here has some cost, same as before. This is the cost C of this edge. Now, if you want to add this edge to your backbone, then you need to pay M times CE. But if you want to just use it as a connection, this is essentially the buy cost. If you want to pay, then you need to pay a factor M more to buy this edge. And that's the thing that I mentioned, rent or buy. So this part, this is essentially rent. And this backbone part is actually the buy part. How much is the cost of the buy would be M times, so we have one cost. This is the rent cost, and M times that would be essentially the buy cost. And this is the case for all edges. That is essentially that makes it uniform. What is the goal you want to that for those edges, for this Steiner tree, you need to pay M times the cost of that because, again, buy cost is M. For all others, you want to connect it essentially to some I star. I star J is the closest open facility to client J. And again, LC of VU is the minimum distance between V and U. So essentially this, this one is the minimum distance essentially. You can see that this essentially is that. You can consider this is equal to C of UV. If you want to rent it, you only need to pay C of UV or corresponding essentially length here. If you want to buy it, you need to pay M times that. So this is essentially connected facility location, but at the same time is a rent or buy problem. And you want to see what is the algorithm that you can do it here. So here I will just mention the algorithm. Again, M is some multiplicative factor that if you want to buy infrastructure, you need to pay this factor M more. This is essentially, this is very similar to this uniform buy at back that you need to pay M more essentially for each edge. Connection cost times M would be the buy cost. I'm giving just the algorithm, very beautiful algorithm here. The analysis we are giving next time. And also we will talk more about Steiner tree and variation like group Steiner tree and others the next session. What is the algorithm for this? This is a magic algorithm. So for each demand J, we will mark it with probability 1 over M. So essentially, say, as I mentioned, assume that D is equal to V. Demands of those vertices which does not belong to V would be 0. So for each demand, guy, I will mark it with probability 1 over n. Let's say this one, the set of marked vertices, essentially. I will construct essentially the best Steiner tree on this. Say there is a vertex where R is an arbitrary rooted vertex. Like this is the algorithm you have for rooted Steiner tree. Essentially, you create, so these guys, these D guys, you will mark some of them at random, each edge with probability 1 over m. This would be D prime. This is D. This is D prime. Then I will find the best Steiner tree according to the cost m times this on these guys. Then for each other guys, I will just connect it to the closest guy here. That's it. Very beautiful and simple algorithm. Just open each guy with probability 1 over m. Very practical. Open with probability 1 over m. Construct the best Steiner tree. What is the approximation? Is the rho of st, which is 1.39. And then connect all others to the closest guy. This is a theorem that we can show. The above algorithm has the approximation 2 plus rho of st is in 1.39. So you get 3.39 for connected facility location. And this is actually, this paper is actually from this very nice paper of Gupta, Kumar, and Garden, Simple and Better Approximation for Network Design in the STAC 2023. I'm not so sure that this has been improved or not. You can check that. But if it's not improved, it would be very nice. So anyhow, this simple algorithm that I have just explained here, connected facility location, just mark some vertices, connect them using a Steiner tree, and then if one goes to the connected one, this has 3.2 plus rho of st, rho of Steiner tree, which is 3.39 current best things for this connected facility location. The analysis is beautiful as well. This is a very simple algorithm with very simple analysis. And that's the thing that makes it very beautiful. We will talk more about it next session. Okay, so I stop here for today's session.